So in addition to having spacecraft, satellites, radio telescopes, we're going to send robots out into the universe. That is the safest way for us to get an object out there and actually study the samples as close as possible before we'll ever have the ability to send a human there. So let's talk about rovers. These are the prime robotic examples that we can discuss. Here we're looking at a picture of Curiosity. So some facts about Curiosity. It was launched in 2011 and landed on Mars in August 2012. Its mission was planned for 2 years. That's it. That was considered a success for Curiosity. Well, here we are in 2019, and Curiosity's still going. Almost 7 years later, and we still have a successful robotic mission. What are the advantages of having a robot? Well, you can get a little more than just photographs. Obviously, the types of photographs you'll get will have a lot more detail, so you'll be able to pull out more information. We understand that the Martian surface is kind of this briny solution in some areas, kind of like this salty, somewhat liquid mix. So, with higher details, we can pull out more information. But more importantly, you can take samples. You can have a drill go down and take a core sample, start analyzing, doing spectrograph analysis of the samples right there, the actual Martian dirt. Future plan missions is to have rovers go out there that can do more detailed analysis, drill deeper into the Martian surface to see what's down underneath there, and in some experiments, some projects, take a Martian soil sample and ship it back to Earth. So that's the power of these types of robotics, and they have been phenomenal successes. At the time of this recording, this will be relatively recent events, but I need to emphasize here that Curiosity was not the first rover on Mars. Another one of its predecessors, was Opportunity, and this is a picture that Opportunity took as it was leaving its landing site. This is what was called Eagle Crater. And you actually can see the tracks as Opportunity went around trying to get pictures of its surroundings, get its bearings correct, make sure everything's operational, and then finally start to leave Eagle Crater. And as a retrospective, scientists at NASA said, hey, make sure to take a picture of where you were, where you've been. Opportunity's mission was a planned 90 days. That would have been considered a huge success. Millions of dollars, literally taking a piece of craft and flying it to another planet for the hopes that it'll operate for just 3 months. The expectation was that the Martian soil, the surface there, the dirt would be so fine that it would eventually get into the gears of the robot and eventually cause mechanical failures. So they expected this robot would only last for 90 days. Well, finally, in February 13th, 2019, almost 15 years of successful operations, was Opportunity officially declared over. We'd actually lost contact with Opportunity in late 2018, but scientists didn't want to give up on it yet. They kept trying to send signals to give it a reboot. Go ahead and start trying to fire up. But on February 13th, 2019, they decided to send one last signal, and it was, Billie Holiday's I'll Be Seeing You, hoping to get Opportunity to wake up, respond back to our signals, and get operational again. That didn't happen, and Opportunity's 90-day mission was officially ended. Now that somber note out of the way, let's interlude with a nice joke and start segueing to other tools that astronomers can use. So the setup here is two cave people trying to discuss what is the fundamental object. And, well, they're going to use a collider. They'll take two rocks, let them roll down the hill, smash into each other, and if there's something more fundamental than rocks, something smaller will crack out of these and fall down into the crevice. Well, 10,000 iterations later, you'll get things like a particle collider. And that's the basic principle. You're going to take what is the fundamental rock, what is the smallest thing that you know of now, smash them together and see what flies out. And that's your particle colliders of these days. Now, all bad jokes aside, let's actually talk about some details here. This is the Atlas detector at the Large Hadron Collider. For perspective, you can see a adult male standing right there in the detector. What's happening is that this is a giant beam hallway for protons, electrons to be accelerated to speeds near the speed of light. Get those things accelerated very rapidly, smash into each other, and this network here, this ring, is filled with all sorts of sensors and detectors. And the goal of these detectors is to see what flies out of the collisions that go through here. See what smacks in there, and then recreate the explosion. With that, we're going to start probing the fundamental nature of the universe, start understanding what's happening in physics under scales even smaller than the protons, electrons. We're going to the subatomic particles. Now, how does this correlate to astronomy? Well, astronomy is dictated by the fundamental physics. Stars are powered by nuclear fusions, atoms being fused together into other atoms. So the better we understand subatomic physics, the better we understand the fundamental nature of the universe, the more information we'll be able to predict about the big astronomical scales. Here's a simplified schematic drawing of what's happening in particle colliders. You can think of it as having one big circle that has protons rotating in one direction in one chamber and rotating in another direction in the separate chamber. So in this top-down view, you'd see the counterclockwise and the clockwise protons rotating around. Now take a side view and you can think of this as being two separate chambers going in opposite directions. Well, what you do for your collisions is you introduce links. And when you open the barrier here, suddenly these guys can finally cross paths, intersect, and collide into each other. So you build your detectors. The tubing here, that's easy. That's just electrodynamical forces. You just need basically a lot of currents, and a lot of wire wrapped up in coils. And you'll create forces that take something like a proton and just accelerate it faster and faster, trying to get it towards the speed of light. You actually can get upwards to like 99.9% the speed of light. So you get these protons rotating very rapidly, and you'll open up the chamber, which I've represented with the yellow square. You'll open up the chamber so that the protons moving very rapidly can cross paths, smack into each other, basically obliterate. And you'll put your detectors all around this region to see what flies out of that experiment. And with that, you're probing subatomic physics, taking those fundamental rocks and smashing them together to see what flies out. Two more things that we can study about the universe. First one will be neutrinos. Now, we'll have a lot more details to share about these in later sections, but I'll give you just the short version. Neutrinos are these light subatomic particles. They are very, very difficult to detect. They don't really interact with a lot of things. Put this in perspective. By the time I have finished this sentence, more than 100 billion neutrinos have fallen through you right now, and you don't feel a thing. Neutrinos don't really interact with a lot of matter. It's what we call a low probability. So to find a neutrino, you need to build very specialized detectors and measure what's called Cherenkov radiation. And that's a wonderful topic of its own that I'll save for another time. Needless to say, there's these type of particles constantly flying out there. The primary source of neutrinos in our solar system would be our sun. It's actually a measurement of how powerful our sun is. Knowing the rate that neutrinos are leaving the sun is basically a diagnosis of how healthy and active the sun is. Now, going beyond neutrinos, we have these wonderful fancy things that we call gravitational waves. And this would be an example of one facility that's designated to try and measure them. And in its most fundamental description, it's just a distortion in space-time. Literally the fabric of space-time having waves going through it. So a gravitational wave is this large distortion, a large ripple in space-time. They were first predicted by Einstein in 1916. And he said, hey, all you need for a gravitational wave is to have very large or very massive objects moving. And that motion will create this kind of ripple. Think of splashing water in a pool. Right? You can do a light paddle, get light waves, or you can splash really hard into the pool of water and see this massive wave ripple on down to the pool. Well, expand that to the scales of the universe. Same thing, where instead of the pool of water, the pool being just water, what's rippling is fabric of reality itself. So, what was predicted by Einstein in 1916 was first observed relatively recently, only in 2017. And from our understanding, it was the merger of two black holes colliding together. And this is data from the experiments trying to say, look, we found these gravitational waves rippling fabric of spacetime. So how did they get this? They use basically laser interferometry. Think back to discussions we've had about how do you measure properties of, say, the wavelengths of lights, right? How big is this light wave? You'll do experiments where you send in a laser source and you'll split the beam and then reconverge it onto a detector and analyze what kind of interference have been produced. Well, for this experiment, imagine trying to use interferometry on the scales of the continental United States of America. That's the sensitivity you need here to try and measure these actual ripples coming through. These are highly sensitive experiments. You're looking for a ripple of space-time that cause distances on this scale to change ever so slightly. So you need to be able to account for, I kid you not, a massive truck driving on the road nearby, because the vibrations on the ground caused by the truck driving will be picked up by your experiments. They're that sensitive. Here's an animation just to depict what we suspect happened to produce the gravitational waves that we measured recently. In this simulation, these are two neutron stars, basically the remainders of stars near the end of their lives. Let's go and get that playing. Now, as they rotate around, you can see these ripples, these waves. This is space-time itself changing as it propagates outwards. Now, as the stars get closer and closer and closer, the rotations are faster, the gravitational waves are bigger and bigger, until suddenly, a giant eruption. They merge together, producing these massive gravitational waves. Coming back to some modeling of the black hole merger that we suspect happened for the gravitational waves that we detected in 2017. Same principle here. Two black holes gravitationally bound to each other, rotating until they finally merge together in one massive object. And we're seeing these ripples of gravitational waves and this giant explosion here once they finally combine. This strain measurement, think of it as trying to tear and compress a sheet of paper, right? You're trying to tear it apart. That can be measured in this strain concept. And this is literal the strain being applied to the fabric of the universe, space-time. The last tool in the astronomer's toolkit that we'll discuss briefly today is computer simulations. What you're looking at right here is a simulation of what you'd see around a black hole, the trajectory of light going around, orbiting this strange behavior. It's due to the extreme gravitational forces. Now, we don't have resolution of black holes enough to see this, and it's highly unlikely that in the lifetime of humanity's civilizations we'll get a satellite close enough to a black hole to detect something like this. So that's the purpose of using the computer simulations, to have the simulations out there to predict. What these simulations are built on are laws of physics. There are fundamental tools that we use to measure things. So you take these equations and see how they apply in these different situations and generate amazing simulations like this one we have playing here. Pulling everything together that we discussed in this section 6, the main properties that matter for us is the properties of light reflecting and refracting off of what material that it's interacting with. With that reflecting and refraction properties, we can build telescopes, either through passing through lenses or bouncing off of mirrors, and process that light so that we can get magnified, enhanced images. Our human eye is the first telescope you can discuss. And as a reminder, we see the universe upside down. Going off of those telescopes, you can talk about the resolution. What's this diffraction limit that you can see? And it depends on the wavelength of light that's coming in, how much it will refract when it passes through a new material, and the aperture. The capital D is the aperture. Think of it as how big, how fat your telescopes are. The bigger the aperture, the smaller the theta, the smaller the resolution. Smaller resolution means that you can see smaller and smaller objects. This refers to the angular size that you're going to see. So you can see smaller and smaller objects for bigger and bigger telescopes. It helps you resolve more things. And we use a wide array of technologies, from cameras to satellites, rovers, particle colliders, to simple computer simulations. All these are tools that we combine together to probe and investigate the universe. So with that, we'll call it into section 6, and we'll see you next time.